1, via.
Okay, good afternoon, everyone. This is the first PhD after the summer break. For those of you who doesn't know what is the PhD, this is a series of seminars where our IEEE members are more in general, the PhD candidates at Politecnico di Torino explain their research to our IEEE members. For today, we will have two important news. The first one is that we came back to our first format, so with 3 speakers. And the reason is that we want a seminar of 60 minutes because we want to ensure 1 credit hour of hard skill for the PhD candidates in electrical electronics and communication engineering. So we want to say thanks to the EEC doctoral board because they give us this possibility. And the second news is that for the first time, we welcome all the IEEE members inside the call. So if some IEEE member want to join the call and to ask a question, this is possible from today and from the next events. So for today, we will have 3 speakers, Riccardo, Francesco, and Gianluca. I would just want to say that the PhD candidates that want to have one credit, they can fill the form that you can find in the YouTube live comments. So please, Riccardo, you can join us by switching on your camera. Riccardo will give a speech entitled Mostly Digital High Fidelity Audio Reproduction Systems. Riccardo obtained both his bachelor and master in electronics engineering from Politecnico di Torino. He had an internship at ST Microelectronics in Aosta in 2015 and worked on a European Industry 4.0 project with the Politecnico in 2017. After that, he joined the VLSI group at the Department of Electronics as a PhD student under the supervision of Professor Maurizio Martina. His main research interests revolve on multimedia digital systems, in particular hardware accelerators for video compression, digital filtering, and mostly digital architecture for high fidelity audio, digital to analog converters. Please, Riccardo.
Hi. Thank you, Yuri. I will share now my slides. Okay. Hello, everybody. As Yuri said, I'm Riccardo Peloso from the Politecnico Torino. I'm here today to talk to you about my work on mostly digital high fidelity audio reproduction systems. I'm from the VLSI lab at the Department of Electronics and Telecommunication under the supervision of Professor Maurizio Martina. So let's start talking about sound. Sound is energy produced by vibrating matter. We humans have a system called hearing that cares about both the time and frequency domains. It has a limited bandwidth, only 20 kilohertz, more or less, from 20 hertz to 20 kilohertz, and a very high dynamic range, from the smallest sound to the loudest one. There are more than 120 decibels of separation. I want also to point out that 2 high fidelity systems can be very expensive. Just the one in the figure is a digital to analog converter that is priced more or less $100,000. Let's talk about digital audio. Why digital audio? Because I have a digital background at VLSI. But also because nowadays digital audio is ubiquitous. We can find it everywhere, and physical audio signals can be easily digitized and stored or transmitted as digital data. For example, we can find a compact disc where there is an uncompressed raw audio data, or streaming services like Spotify, YouTube Music, Apple Music, and so on, that offers compressed audio data. This is a typical audio signal chain. The first part is a microphone that captures the vibrating in the air. Then it creates an analog waveform that is preamplified to match the dynamic range of an analog to digital converter. Then the digital word is given to a digital signal processing part, where it is mixed with other streams. And the resulting digital word is given to a digital to analog converter that recreates an analog waveform that can be amplified to match the energy requirements of a loudspeaker. My work is most on the digital to audio converter part, that is the consumer part, let's say. In the 1980s, with the compact disc, this was the first solution to make a digital to analog converter. It worked at Nyquist rate, so 2 times the bandwidth, more or less, 44 kilohertz, but with 16 bits of resolution. It means that the digital to analog converter needed is a 16-bit one that are more or less 65,000 levels. And so this part should must have the capability of creating 65,000 individual levels of tension or current. Then in the 90s, revolution begins with the called the delta sigma modulator. At first, the initial Nyquist signal is interpolated to achieve an oversampling of n times 44 kilohertz. For example, here I put 3 megahertz, still retaining 16 bits. Then a delta sigma modulator shrink the number of bits from 16 to 1, from 65,000 levels to only 2, so that we can use a 1-bit DAC with only 2 levels, and from 2 levels there can be only one straight line. So it is very linear, this solution, but it has a great amount of noise outside the audio band, and so it has to be filtered out by a low-pass filter. Then the modern solution is similar to the previous one, but now the modulator creates not a 1-bit signal, but 3, 4, 5 bits ones, and then a scrambler converts these bits to individual elements. For example, 3 bits corresponds to 8 elements, 4 bits, 16 elements. Then an 8-element DAC that is 8 individual 1-level DACs are fed with this signal, and the analog waveform is created. As before, we have some out-of-band noise that we have to filter with a low-pass filter. This part in red is all digital, so we can work on it by digital means with automated design tools and so on. It is a very interesting part because this solution is mostly digital, and we can integrate it on modern technological nodes. The first thing to do is the oversampling. Let's say we have the blue waveform, the analog blue waveform, and we want to sample it at the Nyquist frequency. We obtain the red dots. But for the delta sigma to make its magic, we need also the green dots. So we have to recreate the green dots. The oversampling part recreates the green dots from the red ones. Then the delta sigma modulator is the part depicted in the left of the figure. Is a closed loop solution in which a quantizer from 1 to 5 bits, let's say, is embedded in a negative feedback structure. The output is actively compared with the input, and a digital loop filter push the quantization noise created by the quantizer outside the audio band. In the right part, we can see in red the audio signal, and in green the quantization noise created by shrinking the word width from 16 bits to 2, 3, 4, 5 bits. Then we have the scrambler. The scrambler, also called the dynamic element matching part, exploits time domain to even out the usage of each element, each duck, individual duck. As I said before, from 3 bits, we can obtain 8 elements. By even out the element usage, we can embed in each individual element the input signal and help the linearity without resorting to complex analog calibration and design resources to recreate the input audio signal. This is mostly done as a block external to the delta sigma modulator. So working on this topic, I found these main issues. There is the need of an efficient high quality interpolation system. The delta sigma is difficult to stabilize, in particular when dealing with the 1-bit quantizers, because there is a high amount of recirculating noise. The dynamic element matching part is rather inflexible because it's implemented outside the main delta sigma loop. So there is no closed loop system to enforce its working principle. And then sometimes there is the need to directly convert from amplitude to time. And this is done, this can be done by pulse-width modulation and dyadic digital pulse modulation. This can be done without interpolation and modulation, but in a rather straightforward way. The interpolation can be done in 2 domains, the time domain and the frequency domain. In time domain, you can upsample by inserting 0 elements between the available ones, and then apply a high quality linear phase filter that is long enough to ensure the good impulse response in the time domain. So I worked on a novel efficient long digital filter implementation to have a better way to implement this filter. Then the other way is in the frequency domain. You can transform the signal with the discrete Fourier transform, pad with the zeros the high frequency part, and then apply an inverse Fourier transform. Here I worked on a novel mix of discrete sine transform and discrete cosine transform that gave me some very interesting results while retaining the difficulty, the complexity, like similar to the discrete Fourier transform type interpolation. Then I worked on the stabilization of delta sigma modulators. I found that the quantizer inside the loop is made by 2 nonlinear operations, an unbounded quantization and a saturation operator. I saw that the instability stems only from the saturation part. And so I split the 2 and used an aggressive noise shaping only on the unbounded quantization operator. And then the excess noise, I worked on the excess noise using a highly stable noise shaping only on the saturation part. Then I worked to put the dynamic element matching part in the delta sigma modulator. You can see one example in the figure. The output of this system is a shift register like output. When many 1-bit ducks are summed to obtain the final result, the same summation is given back to a global loop filter that feed the pulse-width modulation part, a delta sigma pulse-width modulator. So this closed loop gives us high quality multi-level result. Another circuit I working on is given by a sum of multiple 1-bit delta sigma modulators in parallel, one with different characteristics that are orchestrated by a global modulation loop, a global loop that ensures that the sum of them works as a multi-level delta sigma modulator. Then finally, I worked on the amplitude to time circuit. The DDPM, the Diacritic Digital Post Modulation, is a method developed by Paolo Crevetti at the DET of Politecnico di Torino. I put his work with a multi-level delta sigma modulator and an FIR DAC like in the circuit in the slide before, and I saw that the FIR DAC works by compensating much of the noise created by the DDPM modulator. And the DDPM is very good when in conjunction with multi-level delta sigmas. So the results is a system with low out-of-band total noise. So we need small analog filters to filter out the high-frequency noise. And it is a low-power system due to the simplicity of DDPM and FIR DAC. And it can be ported to modern digital fabrication processes where the analog part is rather sloppy and it can be improved so much by design. Thank you for your attention. If you have a question, I'm here for you.
Okay, thank you, Riccardo, for your talk. It's very interesting. I am asking to all the people who is watching the event to write the questions on the YouTube video. If you are inside the call, you can write directly in the chat or activate your microphone and just talk. In the meantime, I just pose some questions that are already here. The first one from one of our IEEE member is, does the scrambler randomly select the elements or can it also work periodically?
The scrambler works, there are some different types of scramblers. The easiest one randomly scramble them, but the most interesting ones have a noise shaping capability. So each element has its own delta sigma parts, let's say, but they are designed not as delta sigma loops, but okay. In other ways.
Okay, thank you. There is a second question concerning the DEM in the loop approach. How difficult it is to guarantee stability of the global loop?
The stability of the global loop is done by design and simulation. Very problematic part in delta sigmas is that there is the problem of the stability, and you have to ensure it by design. So make extensive simulation of the circuit, and you can, but you can apply, for example, the other stabilization technique I proposed because it's all the techniques I proposed are orthogonal to each other, so they can be implemented in all in the same parts, in the same loop, in the same system, let's say.
Okay, thank you very much. I think there are no other questions. No on YouTube. Okay.
I have a question, if it is possible. I have a question.
Yes, please.
Hi, everyone. Just a curiosity about this type of project. has been already implemented on some boards and some FPGAs or something like that. So there is an experimental part for the for this type of project at the current state of the art. Thank you, Riccardo.
I have here a board that I just received yesterday to populate with components. It has to be attached to an FPGA, in particular the one SoC dev board, development board with an Altera one. And we already tried with some breadboard, but we need now some serious design to try it and measure the power consumption and performances.
Thank you, Riccardo.
Thank you very much. Is there any other question? Okay, so thank you very much, Riccardo, for your talk. We can move to the second speaker. So I asked to Francesco to switch on his camera. And okay, Francesco Marone received the bachelor and master's degree in electronics engineering from Politecnico di Torino in 2015 and 2018, respectively. He is currently pursuing the PhD degree in electronics and telecommunication department at Politecnico di Torino, and his research interests include nonlinear dynamics, neuromorphic computing, and memoristic technology. Today, he will talk about memristors, an overview on the technologies and their compact modeling techniques. Please, Francesco.
Good afternoon, everybody. I'm really glad to be here. Thank you to the organizer for inviting me. It's always a pleasure to share what we do with other colleagues in the near areas of research. So today, what we are going to talk about, me and my colleague Gianluca, who's coming next, is about memristors. I'm more going to dive into what are the main technologies, or at least to give you some hint of what are the main technologies, because it will take more than 3 hours just to introduce them accurately. And then Gianluca will talk more about the architectures and how they're used. But first, let's take a look back at the history of what has been memristors. So when everything started in our field, it was 1971. And there was this guy that now is in his 80s, Professor Leon Chua, that by writing down on a sheet of paper this simple diagram linking a voltage, magnetic flux, charge, and current, he noticed that something was missing. This thing that was asymmetrical, that made that diagram asymmetrical, he decided to call it memristor. Memristor is the contraction of memory resistor. It's a resistor that shows a memory property. And now we are going to explain exactly why. So the original formulation, which is reported on this slide, shows the first, how Chua in 71 with his original paper introduced the memristor. And that introduction, that formalization was an algebraic connection, an algebraic relation, closed or open, analytical or non-analytical, between the history of the voltage and the history of the current at the port. So you have this bipole, which is thought to be a fourth fundamental element, and its conduction properties are determined by how much voltage has been applied in time or how much current has flown through its terminal. You can see it more specifically in the second form, which came out in 1973, I think. And this is obtained in the voltage current domain, which is the can be easily derived by doing the derivation time with respect to time. Here, you can see that the conduction properties, which are determined by the R, so the resistance of the bipole, is determined by the amount of charge that has flown through its terminals. Take care that in the flux charge domain, the relation is algebraic. So you have something that associates to one value of the charge, one value of the flux. While in the current voltage domain, what we experimentally measure at the time of speaking, we are seeing something like loops. When you excite a memoristor, or something that can be considered a memoristor, with a periodical waveform, then you are going to see a frequency-dependent closed loop, a pinched loop, how it was called by Professor Chua. In fact, Professor Chua, now here I'm giving you some hint for whoever wants to dive more into the topic of memoristor taxonomy. There is this really good paper by Professor Fernando Corinto here at Politecnico. And here is also the book he has published a couple of months ago about nonlinear circuits and systems with memoristor. It introduced how the flux and charge can be still relevant for analyzing memoristor-based circuits. But this happened like in 1971. Many years have passed and the interest was like really faded away quickly in the early days. But it was not a big problem because there was CMOS really developing faster and faster. Moore's law was in its golden age. And so there was no need for alternative technologies for computing. And also analog computing was put apart. But then in the last 20 years, 15, someone would argue 10, big data, internet, and so on and so forth, made available a really great bunch of data. This data was of fundamental importance for the development of artificial neural networks, how they're conceived today, that they basically do magic. And the memoristor interest was strongly revived by this resurgence of artificial intelligence. So in 2008, a paper was published by HP Labs in California, The Missing Memoristor Found. By somebody, it's considered a controversial claim because those technology existed previously. But what the authors, led by Stanley Williams, wanted to point out was that theoretical behavior that was theorized 37 years before was finally reconciled with what was the experimental measurements. So let's see some memoristic, experimentally acquired memoristic characteristics. Those are measurements taken for triangular waves on PCM cell, phase change memory. And we can immediately notice that there are two kinds of phenomena. One is the volatile memory, which means that you have sort of resistive switching, which means that the resistance of the device goes from really low to high, but then this effect fades away. This means that a sort of leak integrator exists inside the device, which makes it lose its memory state. And then on the other hand, we have non-volatile memory, which can be observed concurrently inside the same devices. For example, on the lower plot, you can see what is a programming cycle composed of many triangular waves. And you can see that, for example, the threshold switching voltage is moving closer to the origin. So you have a reduction in the threshold switching. You also have, as I will show in a little bit, you also can measure, if you have a really accurate instruments for doing low current measurements of resistance, you can measure a really great holomic behavior at really low field. And this is where the memory is stored. So of course it can be stored, it can be used as a storage device. But let's say that in the last years, in the last 10 years, maybe 3D integration of flash, of NAND flash made the idea of substituting our current technology process for mass production of memories unfeasible, I would say. But as I said before, there is a great interest in neural networks. We want something that can go beyond what are the limitations, and Gianluca will talk about that in a few minutes. We need something that can make our computation boost, can go beyond what is the von Neumann limitation. So there's a lot of interest about spiking neural networks, reservoir computing, oscillatory neural networks, which the memory store serves as a perfect candidate because it can strongly implement neural synapses as in the brain. It also shows many phenomena like volatile memory and non-volatile memory coexisting, which is really typical of the synapses in mammalian brains. Now, let's go more into something more realistic. There are three technologies which are predominant at the moment: resistive RAMs, phase change memory, and spin transfer torque. And there are also many others that I had not enough space or time to cite, but there are also many others under development. Some of them are even on the market right now, and I'll show you one in a little bit. So let's start from one of the two, which I will talk about briefly. This is the ReRAM, the filamentary conduction ReRAM. So what you basically have is an insulating layer between two metal electrodes, and then you have that some sort of ionic species can migrate from one electrode to the other. When the migration of those ionic species reaches the other electrode, a channel is formed. So you go from, as you can see in step one, you go from high resistance states to low resistance states. And then when you come back, you remain in the low resistance state until you reach the point where you apply the opposite voltage, the opposite field. So you're moving back all those ionic species to the other side. And these can happen in many locations concurrently in the device. So by applying many set or reset pulses, you can tune what is the conductance or the resistance of this device. On the other hand, here we have the PCM, the phase change memory. They all basically work in the same manner. There are great developments in the latest years, but the basic working principle is you have a crystalline phase, so some conducting material, and then you have some insulating material in the same, the same chemical species can take both forms. You can think of it as glass, for example. This is a mushroom PCM cell based on GST, which in its amorphous phase, it's a glass, basically. So when you are in completely amorphous phase, you have a high resistance state because in amorphous materials, there's little conduction of electrons. But then when you shrink the mushroom, the conduction properties increase because the path that electrons have to take gets smaller and smaller. So by modulating this ratio between the two phases, you can store multi-level of information on these devices, which are really compact. They can be scaled down to tens of nanometers. This is my main work area. So I spent my first and a half year of my PhD working on this kind of device and on their compact modeling. Unluckily, I cannot share with you the process because it's still unpublished work, so I have to keep it secret, they told me. And I forget to tell you that this is also commercial technology. The 3D crosspoint that Intel ships with its Optane memory boards, it's been confirmed to be a PCM, to be a phase change memory, probably used in its binary form, so 0 and 1s, but still this does not preclude the possibility to use it as a multi-level storage device. The best is yet to come. Yeah, there's a lot of research which I have no time to dive into, but there's many groups working on zero-dimensional, one-dimensional, and two-dimensional materials. Here at Polytechnic, we have Professor Carlo Ricciardi, working on nanowires that implement memoristic behavior. And all those materials are really promising and show something closer to what is the actual synaptic behavior in the mammalian brain. So they're very promising, but maybe in the earlier days. So keep a look. Here I've included also a really recent review about those materials, and you can read. And going to the core of this pitch, I'm just reporting you here what is the second order conduction model for the PCM mushroom. I will not explain it all in detail, but you can clearly see that you first need to compute the field profile, the phi. Then you have to find its maximum. Then you have to integrate that maximum multiplied by the sign. Then you have to take into account all those terms. It's a real mess, I'll say. Then I just forgot to mention you that there are also 3 nonlinear differential equations associated to this little beast. But basically, this is the trade-off that we are making in neuromorphic computing. We are trading like small sizes, so reduce the circuit complexity for really complex devices, which are really hard to model and that show many concurrent phenomena happening at the same time. But this, I mean, this is still a memristor, right? This is the hallmark, as Professor Shua always says, this is a hallmark of memoristic behavior. When you put bipolar wave, a periodic wave on your device, and what you see, what you get from your device is a pinched loop response. This means that you are seeing memristor. And just to be clear, to complete my introduction, here you can see where is the actual memory storage. You can notice those are many ohmic low current IV curves taken for a PCM cell. All those PCM cells were set to different state variable value, which is UA, by the way. It's the thickness of the amorphous dome. And on all those levels, you can store information. You can encode different codes. Now, are complex equations daily useful to us as engineers? Well, I think that this is not the best. They are not the best for our mental health. Let you think solving every time the diode equation with a series resistor by hand. It's like crazy. So there are many tools invented for simplifying our lives, like Bode plots, like IV characteristic for MOSFETs, where you just have to consider where the load line lies on the IV plane, and you have found which is the base point. You have the Nyquist diagrams for analyzing the stability of circuits. So there are all these graphical tools which they all assume some kind of simplification, some kind of compactness of the model. But they are daily useful for engineers who want to design an actual system that works. So, do you expect these memristor, I mean, you cannot answer, but do you expect this memristor to have a really complex differential algebraic equation? Well, this is, for clarity, this is the first memristor that was experimentally proven, let's say. It's the 2008 memristor, works by moving oxygen vacancies inside insulating material. No, this was compactly modeled. It's really simple, it's clear, and it's elegant. You also have many physics-based models which are of indubious utility. When you want to go to really fine detail, you need a really accurate model. But for doing like some quality computation to just understand how the device works. Here, it's really easy. It's elegant. You can see there is a differential equation which dictates the movement of the state variable W, which is the border between the doped and the undoped region, basically where there's a high concentration of oxygen and where there's a low concentration of oxygen. And then you see that the Ohm's law is so simple that it can be integrated. This device can be represented in the flux charge domain, and it shows it can be used to compute the response of those devices in certain region of their operating area. Now let's go back to the PCM, which is my main focus on the side of device modeling. So I cannot show you the actual model because it's still under review. We have to have it published. But what I can tell you is that the basic final step of that model, like for the memories for the transistor, was the to put in place what are the IV curves in order to have engineers designed circuits based on transistors. Here, as was suggested by Professor Chua, we have dynamic route maps. And this is the last slide I'm showing you because I think I'm also out of time. So if you will excuse me. This is the dynamic route map for a PCM mushroom cell. This was also confirmed experimentally. So we have also the experimental part available in the upcoming paper. But you will ask, what does this serve to? What's its utility? Well, I'll explain it in 2 minutes. Here you have the rate of change of the state variable on the y-axis and the state variable itself on the x-axis. So you parameterize those curves on the input level. So you have like 1.61, 1.69, 1.92, 2 volts, and so on and so forth. And you get what will be the evolution of the state variable if you apply that input for an indefinitely long amount of time. This thing gives some really interesting hint inside the working of the device. I mean, at this point, for example, PCMs are programmed by a series of square pulses. So you apply, like, you know, that for after reset, for reaching 12 kilo ohms, you need 100 pulses. So, okay, you apply 100 pulses at 1 volt, 2 volts, and the resistance goes down. But are really square pulses useful for our purpose? I mean, if we had like an ideal short pulse, which goes up to a maximum value and down without any rising edge or falling edge, just something straight, will that pulse be effective? Well, in this plot, I showed that no, they're not the best waveforms, because as you can see, for a fixed voltage level, so when you reach the plateau of your square pulse, then you will have that if you apply that pulse for too long and you're already in a certain region of the state variable, so in a certain resistive state, that pulse is ineffective because as you can see, for example, following the 1.61, the Sayano curve, after you reach that resistance state, which is associated to about 4 nanometers, more or less, then you are not going to move any nanometer anymore because this is ineffective. What physically happens is that you have reached a distance between the heater, the bottom electrode of the mushroom, and the border between the crystalline and amorphous phase, which makes the temperature at the interface too high to have more crystallization, to reduce further the resistance. So what can we get qualitatively from this plot, which is the real important point? That maybe square pulses are not the best. Maybe what we should use is something that has a varying profile, like a triangular wave. Triangular wave will be, for example, the best because it allows to explore an entire region. And if those waves are even controlled with a previous reading of the state variable, then they can be modeled in order to reach the final programming value in a fraction of the time of programming that was initially required. And hopefully somebody will find this research useful someday. I repeat, I am really sorry for not showing you the actual model, but they told me don't do it. And really thank you for your attention.
Okay, thank you, Francesco. I see we already have 2 questions from our IEEE members. The first one is, to your knowledge, do current simulators implement any memoristic models we can play around with?
Yes, there are some memoristic models. You can check the work done by Professor Enrique Miranda at Barcelona Polytechnic University, or Madrid, I don't remember, sorry, Miranda. And he and many others. You can also check the work done by Alon Ascoli at TU Dresden. He also done some really heavy modeling in that regard, like spice models and all those kind of stuff. I mean, this is eventually what we're heading to have like a really good spice models for a PCM cell, which at the time is, there are the industry like IBM who develops this kind of technology as its internal model, but it's hard for them to make them public.
Okay, thank you. The second question is, do you think process variations and technological uncertainties may impact on the final device performance? And if yes, can you consider these variations in the model?
Well, for considering the variations in the model, ask my colleague Luca. He's a statistician. Okay. he knows better than me, but I can speak about the electronic part and what is the technology part. For sure, those have been a limiting factor for the development of this kind of technology. But you know that in artificial neural networks, in all those kind of algorithms, you do not actually need that much precision of the single device. You can compensate it globally. And then there's also another interesting effect, which maybe Gianluca will talk about, that if you have many of those devices, being their characteristic, all stochastic, more or less in the same manner. So we can consider that they are Gaussianly distributed. When you attempt to program them, you have a variation, but it's stochastic, it's Gaussian. When you have like 1 million of those devices that are all stochastic, eventually they will compensate each other. You have like 200,000 that are a little bit higher in conductance and 200,000 that are a little bit lower in conductance. So the final result is higher in precision, in accuracy, than what are the accuracies of your starting devices.
Okay, thank you very much. I see there are no other questions, unless there is some questions from the call. Okay. Okay, thank you very much, Francesco. We can move to the third speaker. So I'm asking to Gianluca to switch on his camera. The first speaker is Gianluca from the Electronics and Telecommunication Department, and he will give a speech entitled A Short Review on Brain-Inspired Computing with Memoristic Crossbar. Gianluca Zoppo received the bachelor degree in mathematics from Università di Torino in 2016 and the master degree in stochastics and data science from Università di Torino in 2018. He is currently pursuing the PhD degree in Electronics and Telecommunication Department at Politecnico di Torino. His research interests include nonlinear dynamics, neuromorphic computing, and NCMC optimization. Please, Gianluca.
So good afternoon, everyone. Thank you for the introduction. Okay, I repeat again, I'm Gianluca Zoppo, and today I will just talk about a short review on brain-inspired computing with memoristic crossbars. So the outline of this presentation will be a very brief introduction to neuromorphic computing, why it is necessary. And then I will just define what is a memristor, as Francesco was doing in the previous presentation. And I will consider one of the different configurations that you may find in the literature, which is called the memristor crossbars. And I will talk about the application in which you can consider these crossbars. So for example, linear algebra, feed-forward neural networks, or recurrent neural network. At the end, I will just show some limitations and briefly conclude this presentation. So as Francesco was highlighting in the previous presentation, some would say that the future of electronics is based on memoristic systems. We know that now the data is growing faster and faster than Moore's law, and so the current memory technologies are kind of a limiting factor. So we would like to have better memory storage, bio-inspired computing, and of course, in-memory computing. So the idea of neuromorphic computing tried to emulate the neural structure and operation of the brain in order to create low-power computing platforms that can be used for different applications. For example, AI application. So as Francesco was really carefully introducing in the previous presentation, a memristor is just a device that was theoretically proposed by Professor Leon Chua in 1971, and then realized in 2008 by HB and Professor Williams. In terms of voltage current characteristic, it's just a two-terminal memristor, and it is described by these mem-conductance or simply conductance, which may depend on a set of first and second order state variables, as you saw in the previous presentation, which are linked to internal geometrical parameters or, for example, temperature. So these are the two most cited articles that you can find in literature. So the first one is the one coming from Professor Chua, and the second one coming from Professor Williams. So the idea today is to introduce you to one of the different architecture that are currently used in this new area, which are called memristor crossbars. These are there is a kind of, the idea is to try to connect these new type of network with the biological bio-inspired approaches. So as you can see here on the right, we have our crossbar in which there are two electrodes. The top electrode, which can consider as the axon that is propagating a presynaptic signal. And then on the bottom electrode, there will be a postsynaptic signal that can compute what is the, for example, matrix vector multiplication of the input signal, and a conductance, which is defined as the synapse of our neuron. So the synapse in our case will be a switching layer, can be defined as a switching layer. And here we can consider all the previously defined devices like PCM or multifilamentary materials that has these memoristic properties. So a first crossbar was actually proposed in 1961 by Steinbuch by considering resistive elements, and he was trying to parallelize matrix vector multiplication using physical laws such as Kirchhoff's law and Ohm's law. Of course, at the time, digital was it was actually not so much appealing, and so digital then became much more famous. But now that we have memristor that can be seen as tunable analog resistors, of course, crossbars are coming again to be important architecture to analyze. So as you can see here on the top left, we have an input vector that we introduced to the crossbar, and at the for each column we will just collect what is the current that is flowing outside, which will define the multiplication by the row of the matrix, the transpose of the matrix, with the input vector. Of course, then you can also change the convert the current into voltage, and then maybe consider it for an iterative process. So if we want to perform a matrix vector multiplication, for example, we need to map our matrix inside the crossbar. So each conductance should be the same value that we want that we should have in order to perform the multiplication. So we want different conductance levels. And here on the top left, we have IV curves showed by an article from Professor Williams, which is called analog signal and images processing, by using large memristor crossbars, in which they were showing that there is a good IV linearity, and this is a good property that we want in our device in order to program them and not to find appropriate, like oscillating or non-linear phenomena in our memristor in the meanwhile we are programming them. As Francesco was pointing out, and also in one of the questions, one of the first variation that we can have is exactly in the programming phase. When we want to, for example, a conductance of 10, I would just use like random numbers, we have to set an interval in which we say, okay, from 9.9 to 10.1, all the values which are lying inside are fine for me, as equal to 10. And if you plot the histogram of the cycle-to-cycle programming variations, then you can see here that this is really, this can be really fitted by a normal distribution. Another thing to consider is, okay, what is the conductance range that we have in our devices, and how can we handle negative values? Because when we have matrix vector multiplication or neural networks, we have to consider also to have negative values. So the first thing to say is, okay, I know that my technology will handle a particular conductance range, which is defined as G off, G on, and we consider a matrix A that we want to map inside the crossbar. So the first thing that you have to do is a linear transformation. You take your matrix and you map it into the crossbar by using a scaling procedure and a translation of the matrix. By doing this linear transformation, all the values that you will have are inside the conductance range, and you can easily, of course, you can program them inside your crossbar. At the end of your operation, you have to perform a recovering step just to obtain the correct results that you wanted in the considered range that you had in your matrix. You also can consider differential pairs of memristor to form, for example, synaptic weight for a neural network. With this structure, you can allow to have both signs, so minus and plus with for conductances, and also you can play with the magnitude of each conductance. So if you want to have some value which are outside the conductance range, you can play with two conductances of the two memristors. So the first application I would like to talk to you is actually the one that we are currently working on, is application in linear algebra. Professor Jelmini proposed this new article in which he was trying to talk about different applications that might come out in some of the computation. Matrix vector multiplication, of course, is the first one, as we were saying before. And then he also considered linear systems and how to compute the dominant eigenvector of a matrix. The last two systems, of course, are working just in some cases, and we are actually analyzing what are the cases in which you can perform this type of linear algebra computation. But the important thing is that all these three computations have a time complexity which depend on the size of the problem. But Professor Jelmini showed that by using a crossbar, you can handle your computation in just one time step. A second application that I would like to talk to you is the feed-forward neural network. Here, of course, is one of the most simple case, but the simplest case, but we have a shallow neural network in which we consider one hidden layer. And we want to map the first matrix of the weight matrix, which are connected input and hidden layers, and then a second matrix in which we have hidden and output neuron connected. As you can see here, we consider differential pair in order to allow to have also negative values. In this article, but there are also other articles which are trying to deal with the nonlinearity functions. In this article, the nonlinear function that you have inside between the two layers was partly software. The result that they showed in this application was, okay, let's start from one of the most famous classification tasks. So we consider the MNIST data set. We unwrap the image and introduce to our conductance matrix. And what we get after collecting all the values which are flowing down by the crossbar is actually the class of the image that you want to classify. Authors claim that they had an inference output of 99% accuracy on the training set, but 97% accuracy on test set, which is actually something that you can also have in software application. The important thing is here in the conductance range, they were claiming that some of the devices were not properly programmed or they were not working very well, but these did not influence the accuracy of what they found. So a third application that we can consider is the application to energy-based models. One of the most famous is the Hopfield neural network. Then we have also cellular nonlinear network. Here comes the idea of, okay, we know that we have many noise inside our crossbars, and in the previous application, the noise is better to maybe to reduce its magnitude. But in this case, noise can be considered to build optimizer solver that use the noise in order to find better local minima. It's very well known that Hopfield neural network are able to solve traveling salesman, pattern reconstruction, max cut problems, so combinatorial problems. But of course, they have a big problem or stacking into local minima. So the noise that is coming from the crossbar can be actually useful here in order to find global minima of our system. So I will briefly conclude with some limitation and pros and cons. So memory store based brain inspired computing is at first stages of life. Of course, this is a new area of research, but this gives us many opportunities and challenges to consider many different applications and many different, for example, learning rules for applying them into our neural networks. When you have heavy computation, such as in linear algebra neural networks, like linear computation, of course, the crossbar can help us to improve our efficiency. There are many research studies, as also Francesco was highlighting, that are still trying to exploit the underlying device physics to emulate brain-inspired computing. This is actually one of our paper talking about a different learning rule, which is trying to approximate the backpropagation update rule, which is actually one of the most difficult things to apply when programming your crossbars. But of course, when you just have to deal with the inference, if you program your matrices in order to handle the inference process of a neural network, then you will have significant improvements in terms of computation time. One of the main problems can be the limiting conductance levels. So if we don't have many conductance levels, then these can affect our precision and also accuracy. And of course, there is still needed further improvements in terms of power dissipation and also scalability issues. So most of the crossbar that we can consider now are 128 times 128 crossbars of memory stores. So we cannot consider like very large problem, but this is something that is kind of studied now. So thank you for the attention. And of course, if you have any questions on the implementation architecture, I would like to try to help you.
Okay, thank you, Gianluca, for the interesting talk. I see 3 questions at the moment. Okay, the first one is any of these applications already implemented and tested experimentally, or they are just theoretical?
So the one, for example, of NNIST classification is already implemented on circuit. And Upfield, now there is a new article in which they are talking about Upfield neural networks where they are simulating and trying to also simulate these on the hardware.
Okay. Second question is, how long does an array preserve the programmed values in current technologies before needing some form of refreshing?
Okay, so I don't have a real answer to this. Of course, there are many problems of for memory. Maybe, I don't know if Francesco knows a better answer because he's working on the on the device application. I don't know,
Francesco, if you want, you can switch on your microphone and your camera.
Sorry, I had some problem with my headphones. So can you repeat the question, because I was a little distracted?
It's how long does an array preserve the programmed values in current technologies before needing some form of refreshing?
Well, there is some resistance drift in current technology. You can measure it, but there are also many clever workarounds. For example, you can search for the projected cells, which are being developed at IBM. And this is, I can speak for my own technology branch. These will solve, when they are correctly implemented, this will solve the problem of drifting. So you basically have like 2 cells and one copies the other. The other is like a sample of the drifting of the first one. So you can compensate that phenomenon and you can solve this problem of drifting. But it's something that exists, and this limits the current applications in networks that need to be reprogrammed every once in a while. For example, I can give you some number. Maybe after a day or 12 hours, the crossbar needs a reprogramming step because the values have drifted for internal phenomena, because you have basically ions moving around, or you have crystal or amorphous phases which relax and lose their original properties. But this is being addressed, and we are really close to a solution for certain technologies.
Okay. We have other questions. Can those structures be used within a backpropagation loop as in a traditional neural network?
Yes. So some research group are trying to implement the backpropagation or other different learning rules. So, for example, also for the Upfield neural network, the Hebbian rule, which can also be iterative. And of course, this is one of the most difficult thing to do, like reprogram every time. But there is also a study in which if when you're reprogramming your memristors, the conductance is not the correct one, which is having some of noise probably by the programming phase. This is not really affecting the accuracy of the system, but this is also something studied in the neural network literature.
Okay. Now we have a very long question. The memristive technology seems to be very promising for neuromorphic applications, in which analog computing is employed to take advantage of the Ohm law to enhance the performance. However, most of data processing nowadays is performed in the digital domain. Do you think that the memristor may represent a good alternative to the CMOS technologies for general purpose computing?
I mean, from my side, yes, but Francesco.
So I don't think that anytime in the next 20, 40 years, CMOS will be replaced in these core domains, which are CPUs and like RAMs and this kind of applications. But there are certain niches like, for example, machine learning, where you need to do so many matrix vector multiplications that the current von Neumann bottleneck is really limiting the software. The algorithms could run order of magnitudes faster and more efficiently on this kind of neuromorphic circuits than they do on CPUs and GPUs right now.
Okay, and we have the last question. Do you think we will ever see a memristor CPU?
I think Francesco already said this, yeah.
I don't think. But Boolean logic is really a fundamental of our current technology, and it will not be replaced neither by neuromorphic nor by quantum. Those are solutions for problems that reason later, but the classical problems that have always been solved really efficiently by Boolean logic and by digital computers, I think, are going to being solved the same way for the foreseeable future.
Okay, this was our last question. So thank you very much for your interesting talk. I asked to all the 3 speakers to switch on their camera so that we can give you a virtual certification. Of course, I hope to give you the certificate at the Politecnico di Torino as soon as possible, a paper certificate. Thank you very much for your talks and for joining this our event. And thank you to all the people who attended the event and to all the people who organized the event and work behind the scenes. Thank you very much, and I hope to see you all. I hope to see you at the next PhD. See you soon.
Thank you.
Thank you.
Yeah.